My name is Kurt Koleski, and I am a fellow at Ohio University. This video serves as an introduction to topographic surveying, spatial interpolation, GIS, and rasters. This video is made possible by the National Science Foundation's Boat of Knowledge in the Science Classroom at Ohio University. Have you ever seen a survey crew while driving down the road? The guy in the foreground has a device called a total station. The guy in the background holds a prism pole over a point. The total station sights in the prism pole to measure distance, horizontal angle, and vertical angle. In order for the survey to be georeferenced, the total station must be set up over a point of known geographic location. Benchmarks are such a geographically known location. They are marked by the U.S. Geologic Survey with known locations and elevations. Anywhere in the world can be designated by a latitude and longitude. Latitudes and longitudes described are in angular units on an ellipsoid such as the Earth. What if we wanted to make a 2D map with distance units such as feet? Projections are advanced mathematical models that convert an ellipsoid shape to a flat 2D map. Using a projection such as a state plane, Ohio South allows the use of an X and Y measured in feet to describe a location in southern Ohio. A total station is set up on a known location with coordinates X and Y measured in feet on the state plane projection. The location has a known elevation of 10 feet mean sea level. The surveyor sights in a prism rod on location P and finds that the distance is 50 feet. All angles must be made in reference to a known line, such as north, and in this case, the angle is 45 degrees off of north. And the angle off of vertical is 75 degrees. Stop the video here and find the location and elevation of point P. Using Pythagorean's theorem and the acronym SOHCAHTOA, the length of the triangle sides and thus the coordinates of the new point can be found. Is this how you completed the triangle? If so, you should have got a new coordinate of x equals 5,035 feet, y equals 5,035 feet, and a new elevation of 10.3 feet at the point P. To actually map the topographic relief of the land, thousands of points may be needed depending on the size of the area. Luckily, we live in an age of technology that simplifies this process. Total stations can perform these calculations on the fly, and Survey GPS can take points with the click of a button. Elevation points must not make a good topographic map. Isolines of equal elevation are called contours. Contours are mapped through interpolation between the points. For example, the 900 elevation contour. The 900 elevation contour would look approximately like this as it travels between high and low points that approximate the 900 isoline. Notice how the isoline is the 900 contour. And stays between the points 872 and 901, 865 and 911, 886 and 903, and so on. And then it finally ends on the elevation point 900. Try drawing the 900, 950, 1000, and 1050 contours on your own. You may pause the video now. If you did it appropriately, your contour should look something like this. What if we wanted to draw contours every 10 feet? We would need to use a different method. Triangulated irregular networks, or TINs, draw triangles that connect points. The area within the triangle is assumed to have a constant slope. Assume a linear transition of elevation along the distance between 2 points. Let's do a couple legs together. So if we took the 903 point and subtracted the 898, that would be 5 feet. We would need 5 equal intervals, or 4 lines separating this line into equal intervals. The slope of this line would be the length of the line divided by the elevation change. The elevation change is 5 feet. The length of the line is 55 feet. 55 divided by 5 feet is 11. Therefore, every division represents a horizontal movement of 11 feet and an elevation change of 1 feet. On this example, we move from 928 to 898. This would mean that we move 4 1/3 foot for every 1 foot of elevation change. Here we can use 2 foot hash marks instead of 1. That way we only have to draw 15 equal intervals, or 14 lines, to separate the 15 equal intervals. Pause the video now and try to get the contours of 900, 910, and 920. If you did it correctly, you should have contours that look something like this. LiDAR is a powerful technology that creates a 3D point cloud of the Earth's surface. LiDAR is a portmanteau of light and radar. Light, or a laser, is emitted from the aircraft, reflected off solid objects, and received by the aircraft. The location of the craft is tracked through a GPS system. How do you think the distance of the object from the aircraft is known? By the LiDAR system. Do you know what the speed of light is? Well, if you know the speed of light, and you know the time that it takes for the LiDAR to bounce off the object and return to the aircraft, then you should know the distance of that object from the aircraft, and therefore know the GPS location of that object. LiDAR captures everything as it sweeps over an area. In order to use LiDAR for our topographic survey, the data must be classified. Look at the point cloud on the left. There are a lot of points within the point cloud that are not ground. Using only the ground data, we can have a very accurate representation of the Earth's surface for our survey. Look at how many more points there are than our original topographic survey. We can interpolate contours by hand for all these points. So GIS software like ArcGIS is used to interpolate the contours. GIS helps to visualize spatial data. When I say spatial data, it only means that the data occupies an area. Contours or 3D point clouds are not always the best way to store spatial information. Rasters convert the chaotic data collection of points and convert it to an organized grid through various interpolation methods such as average and inverse distance weighted. Each cell will be assigned a single value from the point data. Why do we want to use a raster? Well, rasters use universal storage formats such as TIFF and are very storage efficient. Rasters can be analyzed and overlaid with other spatial data for comparison and analytical purposes. Raster cell values can be multiplied, divided, added, subtracted, or other more advanced calculations can be used, such as the slope calculation. Rasters can be visualized in 3D to get a better feel for the data. Notice how the topography of the land becomes more apparent in 3D. Pause the video here and solve the raster cells from the gathered point data using the average technique and the slope equation. Assume the raster cell size is 10 foot by 10 foot. Rasters are a powerful format in GIS. The value of the cells do not have to correspond to elevations. Raster cells can be used for values of temperature, ozone concentration in air, carbon dioxide concentration in air, population, population density, population change. What data would you convert to a raster? Now imagine that you are a scientist interested in declining air quality. You wanted to see if there is any correlation between population growth and bad air quality. Point data for air quality is collected around the country at certain locations. Spatial interpolation can be used to fill the data between points, and a raster could be used to store the data. The raster could then be visualized like effects of urbanization on the environment. Census data at the county level was used to create the map How Populations Grow. Do these maps support your conclusions? If interested in the subjects, effects of urbanization on the environment, and how populations grow, these topics are covered in the appropriately named books, video lessons. Thank you for your time and interest in spatial interpolation.